Good morning, lower sixth. I'm making my own video of this today because I think this section is a little bit more complicated, and I hope my explanations will make it simpler than it could otherwise be. Certainly simpler than the textbook. So we're looking at probability formulae here, and there's nothing particularly new about this, but you will be using these formulae instead of or as well as the Venn diagram techniques that you've already used. Every single A-level question on probability will have something including these formulae, so you need to memorize them, even though they are actually given in the formula booklet, but you need to be incredibly familiar with them. So we have two of them. The addition formula, probability of A union B, is probability of A plus probability of B minus the probability of their intersection. And the multiplication formula, probability of B intersection A, is the probability of B given A times by the probability of A. So that sounds probably quite confusing at the moment. I'm going to explain where the first one comes from. So we had a problem like this in the exercise that I set you last lesson. If we want to know the probability of the intersection, because that's always where we start off with labeling our Venn diagrams, is the intersection bit, we can work that out if we know the probability of each A and B and the union. And I'll show you how we do this. So probability of A union B, that's everything inside both circles, would be the same as adding everything in A and everything in B. But if I added both circles, then I'd be adding this bit twice. So in order to get just one version of everything, I'm going to remove one instance of that. So I'm going to add both circles together, everything in A, everything in B. But then I'm going to minus one instance of the overlap, and the overlap is A intersection B. That means that I don't have two copies of everything in there, I just have it once. And so using this formula, that's exactly the same as this, but actually a more useful version of this formula has this bit as the subject of the formula, because that's normally the bit that we're trying to work out so that we can fill in a Venn diagram. So if I add this to both sides, and subtract that from both sides, I will end up with probability of A intersection B, because I've added it to both sides, what we had before, minus that from both sides. So they look very similar, these two formulae. This is the more useful version, and the one that isn't so intuitive. This one you can see where it comes from. This one is just a rearrangement of that one. So if we ever need to know the intersection, we can do probability of A plus probability of B minus the union. Okay, the second one, again, a little bit more complicated. Probability of B intersection A. I'm going to start off with this bit, and then I'm going to rearrange it afterwards. If I want to know the probability of B given A, that means I'm looking at everything in this circle only. Given A means that I'm no longer looking at the rest of the box. It means I'm looking out of everything that's in circle A, which is probability of A. The bit that I'm interested in if I'm looking at B given A is this section here out of that whole circle. And this section here is the intersection of A and B. And if we rearrange that, multiply both sides by probability of A, you will see that we get probability of A intersection B equals probability of B given A times by probability of A, which is exactly what we had written here. So that's called the multiplication formula because it has a multiple in it, and the addition because it has an addition in it. And simple as that. Right, so I'm going to explain how we would use these formulae with the examples from the textbook. So first example, A and B are two events. We're given probability of A, B, and the union. Find the intersection. That is literally just dropping these into the formula. So probability of A intersection B, this version of the formula. I would write this out every time when you're answering the questions because it reminds you of exactly how the formula works. And then we know what we need is the intersection, so we can just put in the values for each of these. 0.6 plus 0.7 minus 0.9. So we've got 1.3 minus 0.9, which is 0.4 for the intersection there. This example here is going to make use of the multiplication formula. C and D are two events such that probability of C is 0.2, D is 0.6, and the probability of C given D is 0.3. Find the intersection D given C and C union D. For this, I would probably draw a Venn diagram with C and D. It's normally best to just draw a Venn diagram to have an idea of what's going on. So we've got C and D. First thing we're asked about is the intersection. The intersection appears in this formula here, multiplication formula. So we know that the probability of C intersection D equals, make sure you get the letters in the right way around, probability of C given D times by the probability of D. And we know these things, so we've got the intersection is probability of C given D 0.3 times by the probability of D, which is 0.6. 0.3 times 0.6 is 0.18, and that's the intersection. I should actually write that down because that's the answer to the question there. So once you've got 0.18 in there, you can work out rest of C because it adds to 0.2, so we've got 0.02 in here. The rest of D because that adds to 0.6, so we've got 0.42 in there. And the rest of the circle as well. Once you've got that, you can work out probability of D given C. That means we're going to be doing D given C is going to be out of 0.2, and it's going to be 0.18 out of 0.2, and you'll simplify that fraction. Probability of C union D is just adding all of these together in the middle. Okay, so that explains that bit. The rest of it's in the textbook if you need to check over the answers to that. But there are two more important conditions, special cases, that I need to bring your attention to. So I would also take a note of these and write them down clearly somewhere, because a lot of the time an exam question will mention either mutually exclusive or independent, and you'll have to use this information to be able to answer the questions. So remember that with mutually exclusive events, A and B don't overlap. They cannot happen at the same time. So the special rule for mutually exclusive events is that probability of A union B is just the probability of A plus the probability of B. Circle plus circle, that's the union. There's no overlap to subtract, so there's no minus anything there. For independent events, probability of B given C is just the same as the probability of B. I don't know why I've chosen B and C there. It's normally A and B. So probability of A given B is just the same as the probability of A. That just works logically. If B doesn't affect A because they're independent, then the probability of A given that B has happened is exactly the same as the probability of A. It doesn't make any difference. So we can sometimes use this together with the multiplication formula to answer some difficult questions with independent events. There is one thing that a lot of people seem to have got the idea that events are either independent or they're mutually exclusive. That isn't the case. You can have events. So I was going to write this down. You can have events that are neither independent nor mutually exclusive. There isn't a special word for those. But I know that some people have been thinking that they're either one or the other. They're not. If they're mutually exclusive, they're definitely not independent. If they're independent, they are definitely not mutually exclusive, but there is this third category that doesn't really have a name, just events that don't fall into either category. Okay, that's it for today. Good luck with the exercise, and as always, send me questions if you need help with anything.